Okay, so today we're very glad to have Dr. Rayanne Luke as our speaker to the numerical analysis seminar. Dr. Luke is a postdoc fellow working jointly with Johns Hopkins University and the National Institute of Standards and Technology. So she received her PhD in applied math from University of Delaware, and her work focuses on like various like mathematical modelings that connect to the real world data in the realm of mathematical biology and medicine. So today she's going to talk to us about parameter identification for tear film thinning and breakup. So the floor is yours. Thank you.
All right, thank you very much for the introduction and the invitation. I'm excited to be here and share some of the latter half of my PhD work with you. So I am now a postdoc at Johns Hopkins. So if you didn't catch this earlier, I will tease a little bit of what I'm doing now at the end of this in case you're ever interested in hearing more about that. So let's see. Okay, so first, some of you may know the University of Delaware has a pretty rich tear film research group. So these are sort of the old folk that have been there and been around for a while. There are a handful of undergrads that have joined us from time to time on this work. So some of you may know this is my PhD advisor, Rich Braun. And these are our collaborators from Indiana University who did the data collection that we use. So the first half of this talk will focus on the work done by the people in this upper half part. And then I'll talk at the end about some of the more recent results and work that the group is doing right now that is in the realm of machine learning. Okay. So to jump in with a little bit of background on the tear film, the human tear film is a 3-layered film. The majority or the largest layer is an aqueous layer, which is mostly water, which sits below a thin, oily lipid layer that protects the eye against evaporation. And sitting on the ocular surface, there is this sort of mucin forest. To give you an idea to scale, here is a side view of the eye. So the aqueous layer is on the order of a couple microns, and the mucin layer and the lipid layer are on the order of nanometers. And this is all happening on this very, very thin layer of fluid on the front of your eye. And our big motivation for why we study this is we would like to understand dry eye disease. And so our work deals mostly with those that are healthy patients, so they don't have dry eye disease, so that we can best understand the control subjects first, and then eventually move to look at this condition. So before I get into a little bit of what dry eye disease is, first I have to tell you what tear film breakup is. So simply put, it's a thin region formed in the tear film. Optometrists instill the molecule sodium fluorescein into the eye, and then they will image them. This is a fluorescent imaging, in order to see characteristics such as how fast breakup forms and what shape they are. So I've highlighted here on the cornea a couple regions of tear film breakup. Those show up as dark regions. So if there is more fluid, then the tear film will glow brightly. So the big question we want to answer is, what is going on in the breakup regions? Is the tear film very salty there? Is the ocular surface inflamed? And currently, there is no real way to know except by modeling. So this is where we come in. So now that you know what tear film breakup is, I can better explain dry eye disease. So this is a very prevalent condition based on your diagnostic criterion. It affects up to half the population. Simply put, it is when the eyelids and the tear film are failing to protect the eye, and it is characterized by tear film breakup, which I just introduced, very salty tears, which is called hyperosmolarity, and inflammation of the ocular surface. Current treatment methods typically take a stepped approach. So depending on the type of dry eye that you are diagnosed with, you might change your diet to include anti-inflammatory foods. You might use artificial tears if you are found to have low tear volume. And if a lot of things don't work for you and you go down this step procedure, you might end up using an amniotic membrane, which has been described to me as a Band-Aid for the eye and doesn't look very pleasant. So we would like to try to address the underlying causes of dry eye disease, which the treatment is currently only addressing the symptoms. So those underlying causes or mechanisms are evaporation and lipid dysfunction, which thankfully we build into our models. Okay. So this is our solution to this problem. And I'll remark that this is relatively new. To the best of our knowledge, the work that I started and that the group has continued is the first of its kind to do a tight comparison of models for tear film thinning to data. Okay, so now I'll introduce the model. So it's a PDE model, and it's going to be based on the Navier-Stokes equations, and we're going to take a lubrication theory approach to simplify things. So the model is going to build in those mechanisms that I talked about, both evaporation and lipid dysfunction. Evaporation is something that you can probably understand pretty easily, but lipid dysfunction, or more specifically, the Marangoni effect, needs a little bit more explanation. So a little video will help us out here. So once this loads, on the left, we have water. On the right, we have soap. The idea of the Marangoni effect is that it's all about a difference in surface tension, okay, or concentration. And so on the left, we have pepper flakes to show movement. The soap is going to have a lower surface tension than the water. And so when we add it to the water, it is going to induce couette or dragging flow and pull the water tangentially outward. And so that's illustrated by those moving pepper flakes. Something that differentiates evaporation and the Marangoni effect. Evaporation typically acts on a relatively long time scale, whereas you saw in this video, the Marangoni effect is a matter of a couple tenths of a second. And so those time scales will be built into the model, and we'll be able to differentiate which mechanism is dominating the tear film breakup. Okay,
Excuse
so let's
me,
get into
can
our
we
modeling.
ask questions, or should we wait till the end?
Sure, go ahead.
What was the purpose of the soap in this experiment? What happens to the soap?
So the soap is going to act like the lipid layer here. So it is, it has a lower surface tension or surface concentration than the water. And so there's a difference then when you add it to the water in surface tension. And so there's a gradient basically, and that's going to induce this dragging flow outward radially.
I see, thank you.
Yeah, so you think of the soap when you think of the lipid layer in subsequent examples. Yeah. Okay. So the goals of our model are to model the mechanisms that affect tear film thinning, and in a related capacity, identify parameters that can't currently be measured in patient trials. So I mentioned we're going to start with the Navier-Stokes equation. So we'll model the tear film as an incompressible Newtonian fluid. We're going to focus our modeling efforts on the aqueous layer. The mucin layer and the lipid layer will be boundary conditions. And we're going to use lubrication theory to greatly simplify the Navier-Stokes equations, because the aspect ratio comes from the length along the eyes, maybe on the order of a centimeter, whereas I mentioned before, the thickness of the tear film is only a couple microns. So that ratio is very, very small, and we lose a lot of the terms in the full Navier-Stokes equations. Okay, so this full model here was first described by my academic big sister, Lan Zong, in 2019. So we'll begin with the aqueous layer. So here we have the tear film, the air, and then the cornea. So here's a pictorial representation of the model, and now let me explain everything. So we have an evolution equation for the tear film thickness or height. It's governed by evaporation, flow, and osmosis. So that's water being added from the cornea. The pressure of the fluid is related to the curvature of the tear film. And we model transportation of salt or fluorescein ions with a transport equation. So advection, diffusion, and then osmosis and evaporation are also a part. This is a model in axisymmetric coordinates. We also have a similar one in Cartesian coordinates. So here we're going to use symmetry at the origin, no flux at our outer boundary conditions, and our initial conditions will end up all being uniform. Okay, so that's what's going on in the tear film. Now let's talk about the influence of the lipid layer. So in this model, we want to model lipid dysfunction. So we hypothesize that a glob of lipid is sitting on top of a region where tear film breakup will form. And again, it's going to act like the soap. It's going to induce a change in your concentration. So there's a high concentration of lipid sitting right here. There's a low concentration of lipid here. And the lipid wants to return to a uniform concentration. So it's going to drag fluid out from underneath as it moves and create a breakup region. And so this, we have two types of flow that come as a result of this. So directly related is Marangoni flow or dragging couette flow. And then there's pressure flow. So the lipid concentration is modeled by another advection diffusion equation, diffusion and advection here. And this transition function is just telling you it's a smooth approximation from outside the glob to under the glob. Okay, so we usually just use a tanh. And then we have two fluid velocity terms. So we have a depth averaged horizontal fluid velocity and then a surface horizontal fluid velocity. They're relatively similar in that they are a combination of inward pressure flow and outward Marangoni flow. So there's this sort of competition going on. So the pressure flow is trying to fill in the spot. That's a capillary flow or Poisson flow. And the Marangoni flow is outward or dragging couette flow. So it's starting to form the spot. And so these are going to compete, and whether one of them dominates can help us understand which mechanism is the main driving force behind the breakup. Okay, so I've told you a model that has to do with tear film thickness, things going on inside the tear film and the lipid layer. And I originally showed you in a video of the fluorescent tear film. So we need to connect the two because I can measure intensity, but I have equations for film thickness, pressure, etc. So I got partial differential equations for all my variables. We choose to solve this using spectral collocation in space. And then we end up with a differential algebraic equation because the pressure equation does not have a time derivative. It's a relatively stiff system, so we solve this with a stiff solver in MATLAB. And then from this, there's an equation that relates tear film thickness and fluorescein concentration and fluorescent intensity. So once we solve the system, we compute fluorescent intensity, and then this gives us something to compare to the experimental values that we extract from the videos. Okay, so first, what do the non-dimensional solutions look like? So on the top here, I have fluorescent intensity on the left, film thickness on the right, and arrows are indicating increasing time, so you can see the formation of the spot. The first thing to notice here is the qualitative similarities between intensity and film thickness. We can measure an experimental intensity, compare it to our theoretical intensity, but then we want to make conclusions about what's happening to the film thickness. So thankfully we can do so because they're very qualitatively similar. Next, we have pressure, which I mentioned before is related to the curvature of the tear film. Next, I have both of my solute concentrations. So C will be the osmolarity or the saltiness. This is a normalized fluorescein concentration. And you'll note that they have a sort of inverse relationship. So as the tear film thins in the center, there is less water, and so the concentration of solutes goes up. Finally, this is our lipid. So the high concentration in the center is indicating where the glob is. The low regions outside are constant, and then there is diffusion outside the glob. And this simulation was created with using uniform evaporation. Sometimes we choose different evaporation profiles. And to give you an idea of the time scale that we're looking at, this was done for a final time of 3 seconds. So this is sort of an intermediate breakup. It's not quite as fast as we saw in the video, where the pepper flakes dispersed on the order of a couple tenths of a second. And it's not super long. Sometimes people are able to hold their eyes open for these trials on the order of a couple minutes. So that would be, this is sort of a mixture of the two. All right, so now I will get into how we compare our models to the data. So a couple notes first about how we do our optimization. In order so that the boundary conditions don't affect what's going on with the tear film dynamics, we're going to widen our computational domain. And for all of these optimizations, we are conducting a nonlinear least squares minimization. I added a second order finite difference approximation of the Jacobian to improve performance. And to get an initial guess, we run forward computations of the model until we get something that looks reasonable, because we have parameter ranges that we sort of think are physically realistic. Typically, we're just going to use default tolerances, and most of the time we get convergence because the change in residual meets our tolerance. Okay, that looks a little funny. Sorry about that. So just to say what we use in terms of our algorithms, there's nothing too fancy that we're using, just built-in MATLAB solvers. So we're either doing an unconstrained or constrained optimization. For unconstrained, we've tried using fbin search, which uses the Nelder-Mead algorithm, as well as LSQ non-lin, which I have focused on. In particular, you've been using the Levenberg-Marquardt algorithm. And then there are times when we decided to constrain certain parameters. For example, some are not physically realistic if they are negative. So in that case, we'll still use the LSQ non-lin function, but using a trust region reflective algorithm. Okay, so the first thing that I did very early on in my PhD was to validate that our optimization procedure could give us realistic parameter estimates. So I did this for either tear film thickness or fluorescent intensity. From here on out, we will focus on fluorescent intensity. Generated an initial guess, added some noise to mimic the data, conducted the optimizations. We, over the course of the time, varied anywhere from 1 to 5 parameters. Eventually, we were able to reduce the number of parameters that we needed. And we found that we could add up to 20% noise, but our optimal parameters still stayed within about 6% of the ones that we used to generate the solution. So we took this as a good indication that our optimization was finding the right, the true parameters. And in terms of comparing the algorithms, we found that the Levenberg-Marquardt and the Nelder-Mead algorithm gave results that were essentially identical, but we tended to use the Levenberg-Marquardt algorithm because it was several times faster. And to give you an idea of the time scale of these optimizations, some of the fastest ones were a couple minutes and some of the slowest ones were maybe 2 hours. Okay, so how do I actually conduct the optimization? So here is, over time, a plot showing you the spot forming. So the first step, the data is very noisy. So we're going to apply a Gaussian filter. We're going to extract data and then do some alignment because people's eyes move a little bit. I'm only going to use a certain number of time levels. As you can see, there are many, many to choose from here. And extract the data. We separately found a way to estimate the initial tear film thickness and the fluorescein concentration. And we put these all together into our optimization, which is simply minimizing the difference of the theoretical and the experimental intensity over our parameters. Then, of course, we ask if it converged. If not, sometimes we had to change our initial guess. Sometimes we had to change the model, which I mentioned before. We have several different evaporation distributions we used, for example. And if it did, then we were glad. We recorded the values and those of the theoretical quantities, such as the parameters. And this, as you might expect, is a relatively delicate procedure, especially working with data. Things don't always go right. So over the course of my PhD doing these PDE fits, I only fit 20 instances. So there was a lot of work on the data preparation side. Okay, so let's fit some actual data. So if this video plays, it will show a faster breakup than the one I showed at the beginning. And these sometimes have trouble playing on my computer. I apologize because they are so large. We have extremely great spatial resolution on these videos. All right, let me try it one more time. Okay, so you can see a little bit, there's some breakup happening here. I'm going to actually focus on something that's currently being obscured by the upper lid. So here's a nicer picture of that. You can see there's a very nice circular region here that I'm going to fit with my axisymmetric model. So I'm going to extract data from a line across that breakup region, and I'm going to do so for every time level. As I mentioned, I'm going to minimize the difference between the experimental and the theoretical intensity, and I'm going to do so over 3 parameters: the evaporation rate, the size of the glob of lipids sitting on top of the breakup region, and a parameter that quantifies the relative strength of the Marangoni effect. And in this situation, we are using a profile for the lipid glob where we have a high evaporation rate under the glob and no evaporation rate outside the glob. And this may seem counterintuitive, but research has suggested that the organization of the lipid is highly connected to its ability to prevent evaporation. And we hypothesize, and there's actually evidence that shows that lipids may be very globs of lipid may be very disorganized. And so they do a poor job of preventing against evaporation. And there is evidence showing that breakup regions form under highly concentrated regions of lipid. So here are some results, some takeaways from this optimization. You may have noticed on the previous page that the experimental data started much lower than a uniform initial condition, and this is because the person's upper lid was obscuring the breakup for a couple seconds. So we remedy this by using what we call ghost time levels, because our model needs to start with an initial condition, and after that, we start comparing to the data. So some takeaways are that this is pretty significant breakup because the tear film thickness drops almost to 0 in the center of breakup. Our fluid flow profiles show that there is significant outward flow. And if we compare our evaporation rate to thinning rates, these were taken experimentally, just targeting the center of the cornea, not necessarily looking for breakup. We see that our evaporation rate falls within this distribution. But more specifically, we should compare our overall thinning rate because we are able to separate the effects of evaporation from the overall thinning rate. We still see that our overall thinning rate falls within the distribution. And because the overall thinning rate is faster than the evaporation rate, it's another indication that there is significant outward flow. Evaporation plus outward flow are contributing to the breakup. Okay, so some takeaway results about our PDE models. One big thing we would like to do with our results is use them to tell us which mechanism is dominating the tear film breakup. So there are a couple of different things that we look at in order to do that. One thing we look at that I mentioned before is the flow direction. So pressure dominated capillary Poisson flow is going to be directed inwards. and that is characteristic of evaporation-dominated thinning. In contrast, outward Couette dragging flow is indicative of the Marangoni effect, and that will be Marangoni-dominated thinning. So if we have an example here on the left, where the flow is inward and weak, that was going to slow thinning down because it's acting against the thinning. And it suggests that evaporation is dominating the thinning. In contrast, if we look at flow that is outward and strong, that's going to speed up the thinning, and it's going to suggest the Marangoni effect is dominating. And so just by looking at the flow direction, we can get an idea of which mechanism is dominating the breakup. Something else we look at are thinning rates, both evaporation and overall thinning. So first of all, the plot on the left is our evaporation rate. And so first I'll mention again that this is new, that without modeling, you are not able to separate the effects of thinning from evaporation from overall thinning. So we're able to separate the effects of evaporation and flow in particular. So the first two colors here, green and blue, are from the model that excludes the Marangoni effect. And then this yellow is from a model with both the Marangoni effect and evaporation. And again, we are comparing to these point measurements that were taken in the center of the cornea. So I mentioned it's more realistic to compare our overall thinning rates because this paper was not able to separate evaporation from overall thinning. And the blue here is going to be the model without Marangoni effect, so just evaporation. And the yellow is going to be with both evaporation and the Marangoni effect. And we see that there's a difference. There's a separation of the two, more or less. So when you add in the Marangoni effect, when it is a better model to fit with, you have slower thinning if it's evaporative, and you have faster thinning if it's Marangoni driven. So this is another way to tell which mechanism is dominating the thinning. And one final thing we look at that is very important to clinicians is the saltiness or the osmolarity. This is very important because it is part of the dry eye diagnosis, but they're only able to measure the salt levels near the lower eyelid. Wouldn't it be nice to have a way to estimate salt levels in tear film breakup, since tear film breakup characterizes dry eye disease? We can do this with the models. So our results show in particular that we don't reach quite the concentration of seawater, which would be about 1,000 milliosmoles. But in particular, our model with evaporation and the Marangoni effect, which acts on an intermediate time scale, but under 10 seconds, still has a relatively high increase in salt concentration in only a few seconds. And this was a bit of a surprise to us. We also thought that salt concentration may go with trial length, but we found that this is not the case. There is some sort of leveling off that may occur that we attribute to diffusion. So eventually, once there's enough buildup of concentration, diffusion is just going to reach an equilibrium, removing it from the breakup region. Okay, so those are some takeaway results from our PDE models. So we started out validating our PDE model optimization with synthetic data. Then we showed that our PDE models find realistic, physically relevant parameters. Now we are going to validate simpler ODE models against our PDE models so that we can work towards automating the fitting procedure. So here are the elements of the PDE model, and some of them are going to get simplified, some of them are going to get dropped. So advection will no longer be nonlinear. Diffusion is ignored. And we're going to combine our lipid-induced tangential flow and pressure-induced tangential flow together into a simple extensional flow term. So we have a hierarchy of ODE models that we consider. One that's very simple is constant extensional flow. So your flow term U would just be A times your parameter or your variable X. So what does this look like? If A is positive, this is like stretching taffy. Your taffy is not moving at all right at the origin, but it's moving a lot far away at the ends. And we have a very simple ODE for this. We have a flow term, osmosis, and constant evaporation. If we instead introduce a time component into our flow, we can replace a constant A with a decaying exponential. And so then it's as if we're pulling taffy, and then we're not pulling it quite as hard, and then not quite as hard, and eventually it dies off. And this is a very similar, you'll see exactly where the components of the flow term come in to give you your model. We can also put these together. Go ahead.
Sorry. Can I ask a question about the ODE model?
Sure.
Should I think of it as a approximation to the PDE model near the region when your H is very small?
So it's not necessarily when H is very small. It is instead of looking with a spatial component on a line across the breakup region, only looking in the center of the breakup region.
Ah, I see. So like there could be like small like cusp or something. Okay, thank you.
Yeah, I'll have a picture of that in a minute too. So if we put them together, the constant and the decaying extensional flow, we again have a very similar looking model. And these last two are designed specifically to model Marangoni flow, because as we saw with the example with the pepper flakes, the tangential flow is very quick and then stops. So we wanted to be able to model that. So we will fit just the very center of a breakup region with this model. And we will do so over 4 parameters that show up in these models: a constant evaporation rate, and then 3 flow terms. Okay, so here are some results. So the blue curve is a little hard to see, is our experimental data. And then we're fitting with a hierarchy of our models. And we include the central data from the PDE just for comparison. So here's a table with a lot of numbers that probably don't mean a lot, but I will tell you, and you can definitely see that if you just look at the norm, these 2 models are doing a way worse job than any of the others. And I'll tell you that these are unrealistic evaporation rates. So this is an indication that this breakup cannot be explained without flow. These 2 models only have evaporation and osmosis. If we look at the flow terms of the models with flow, the values are all positive, which signifies outward flow, which hopefully if you've been following along well enough, you'll know that this is suggestive of the Marangoni effect. So this breakup is probably driven by the Marangoni effect. And in particular, if we look at our best fit model by norm, it's a model with a very small evaporation rate and decaying exponential flow, which should mimic exactly what we saw with the pepper flakes when soap was added.
Excuse me.
Yep.
On the previous slides, if I just look at the norm of the error, it seems like PDE is having a slightly higher norm than the ODEs. I would have expected that the PDE would be very good and the ODEs would be rather simplified, so a little higher, or how should I understand that?
Yeah, it's a good question. So the PDE, you have to remember, was fit to not just the data at the origin, but across the whole line. So that fit is done in time and space.
Oh, right.
So the PDE had to fit a lot of, it had to fit a lot of other data points that aren't shown here. So
yes, that makes sense.
Yeah. So it's included to show the comparison, but you certainly have to take that with a grain of salt. Yeah, good question. Okay, so this is one that is in contrast to the one we just saw. So we fit with a reduced number of models here. And just by the norm, we see that the best model is one that is purely evaporation. There is no flow and there is no osmosis. If we look at the models with flow, they have negative flow rates. So this is suggestive of inward flow. And so this is characteristic of evaporation-driven flow. We have a relatively significant evaporation rate, and if you included flow, it would be inward. Okay, so I did this for all of my PDE fits, and I found good agreement of the ODE results and the PDE results. So I had 12 instances that I fit with a model that was purely evaporation-driven thinning, so the Marangoni effect was not included. These were relatively slow trials in comparison. And I fit 8 instances for a combined 20 total, with a model with both evaporation and the Marangoni effect. In the first case, I found that 8 of the best were fit without any flow at all, just with evaporation. And the other 4 for their best fit had inward constant extensional flow, which is characteristic of evaporation-driven thinning. On the other side, all of the models were best fit with models for time-dependent flow, which is characteristic of the Marangoni effect. So this is a big thumbs up moving forward. Now that we want to automate the procedure, we want to use ODEs because I was only able to fit 20 instances because it takes a lot of work to find a breakup region that is circular enough to be fit with our axisymmetric model or linear enough to be fit with a Cartesian model. And breakup is just not simple. So we wanted to fit just the centers of breakup regions so that we could extend this on a much larger scale and work at getting population level results. So just to wrap up here, there's some takeaways from what we can say about PD and ODE results. Most of them are in agreement. So first, we see that the evaporation rates overlap, although some of the evaporation rates are a little bit larger. If we look at the distribution of minimum tear film thickness, it's relatively similar. Again, we have a relatively small sample size, so it's also hard to make large conclusions. The one where there's the most variation is in the osmolarity. So we see that the maximum osmolarity is larger on average for ordinary differential equation cases, but this should be expected without diffusion. In the PDE case, diffusion is allowed to pull solutes away from the center of breakup once it reaches a certain concentration. We have ignored that effect with the ODE models, so we do expect this difference in results. Okay, so this is sort of the new, shiny, exciting work on automation and which the tear film group is still continuing on. So this has been going on for a little over 2 years now, although we have some exciting recent results to share. So we've been using machine learning to first automate the detection of breakup regions, and then go ahead and fit with our ODEs. So we have a large team that's involved in this. They trained a convolutional neural network following a paper by Su et al., who did something similar, but not quite the same. And what they did was they classified all of these image patches. This is an example image from the original Su et al. Paper. We wanted to classify them into 5 categories, whether they had eyelashes, tear film breakup, non-tear film breakup, the sclera or the white of the eye, or the eyelid. And we are going to be focused on breakup, but we of course need to make sure that it can distinguish between breakup and non-breakup. So the team worked on using over 50,000 of these image patches, and they did this all by hand. And we achieved a breakup classification accuracy of 93% when we tested this, and a non-tear film breakup accuracy of 96%. So we're pretty confident we can identify breakup, and we're pretty confident that we know what is not breakup. So we took this And now we're going to do automatic fits that look very similar to what I was doing manually. So this blue box here is a highlighted region where the convolutional neural network identified with greater than a 99% probability that there is breakup. And what we did is we extracted fluorescent intensity from the center of that box. And this is what it looked like. So one thing that we did was we optimized where to fit. Okay, so you don't want to fit when the tear film is, if the intensity is increasing for some reason. Again, data is noisy. And then we fit with our hierarchy of models and try to make mechanistic conclusions. So in this case, this example was best fit by zero evaporation and strong outward and decaying tangential flow. And hopefully, if you've been following along, you'll know that this suggests that the breakup is Marangoni flow dominated. In particular, if we look at these two models that don't have any flow, they do a very poor job of capturing the dynamics of the experimental data. So further evidence that flow is important in this instance. Okay, so here are some new exciting results. So this has been done now on more of a population level. And some of the questions that we want to answer include, can we differentiate what's going on between subjects? So here are 4 subjects for which there were a handful of breakup instances across different trials that they sat for. And what we are plotting is the flow rate against the evaporation rate. And we're trying to see what sort of patterns emerge. We notice here that the lower 2 subjects, their plots are clustered near the origin. And this is in contrast to the upper 2 where it is much more scattered. So this might suggest that the lower 2 have a lot of breakup instances that share very similar characteristics, whereas the other subjects have a range of breakup instances, some of which have very large evaporation rates, some of which have very small and strong strain rate parameters. So the distribution of parameters seems to separate even some healthy subjects. And so in particular, we noticed that we observe some of the same characteristics like fast breakup that we might expect from dry eye patients. So this is something that we're going to have to be careful about if we then apply this to dry eye data. Something else that we look at is the results, the aggregate results of all the fits. So these are going to be Model D results. I'm reminding you of what Model D is. It's that decaying flow, osmosis, and constant evaporation. So there are 467 fits to analyze. This is giving us great population level statistics for healthy patients. Some of the distributions are very satisfying. You might expect, for example, that evaporation rate in healthy patients shouldn't be very large. That would mean that your eye, the water on your eye is rapidly evaporating. So in healthy patients with good tear films, yeah, we would be happy if the evaporation rate clustered near 0. Some of our results, however, might not be physically realistic. So D here is your initial tear film thickness, and finding initial values above 6 microns might be outside the scope of what we think is realistic. So might be some work to do there still. But overall, we're very happy with these results. We have a nice distribution of our strain rate parameters that has a fairly, it's nicely tightly clustered at a slightly positive average. And one other thing we can look at from all of our subjects is we can look at our final time osmolarity and see if we can connect it to any of the other parameters. So if we look at the relationship between final time osmolarity and evaporation rate, we notice that there aren't any low osmolarities at a high evaporation rate. So there's some sort of trend here. I originally thought it might be linear, but with the addition now of more data, maybe it is cubic, maybe it's logarithmic, not really sure. Maybe that might need more data to flesh that out more. But there's definitely some sort of trend. And similarly, there is another trend between final osmolarity and initial strain rate. So we see that there are no high osmolarity values. They're all very low at high outward flow rates. And so that is related to, if you have a high outward flow rate, typically the thinning is occurring very fast and evaporation doesn't have time to act. And it's also related to, if you have a very high flow rate, you typically have a very low evaporation rate. And we definitely have a strong connection between evaporation rate and osmolarity. So still some analysis to be done, but some promising results so far. So in my last bit here, I just want to compare to what I've done. So this work is the current tear film work, and this, I believe, was just scrubbed from my thesis. So these are my previous fits. The blue is the automated fits, and I mean, I did a far fewer fits, so you might expect there's going to be a lot more variation in my results with a lot less smaller sample size. But we see a much better comparison if we look at the current tear film group results and our experimental thinning rates. This is from that study that I mentioned before, where they looked at the thinning rate in the center of the cornea. And there's pretty good agreement here. So this is encouraging that our model results are doing a good job of capturing physically realistic dynamics. But again, we do expect to have some faster thinning rates because this study did not target breakup. It just looked at the center of the cornea. So we would expect if you're focused on breakup, you're going to look at faster evaporation rates. Okay, so let me summarize here with what's been achieved and then some future directions. So we are able, by fitting with our models, to determine which breakup instances are active and which one is the dominant mechanism. We can estimate relevant parameters such as evaporation rates, strain rates, final osmolarities, etc. We were able to, as an important step, validate the ODE models against the PDE models to pave the way for this automation. And now we've had some very fruitful results from the automation looking at population level results. In the future, there is a wide range of things, of directions we can take this, but a couple are, maybe the next logical one is to extend to the dry eye and perhaps even to making this something that could be available in a clinical setting so that clinicians could use this in real time to look at their patients and understand whether they have dry eye, whether they don't, maybe what mechanisms are involved in their breakup, and that might suggest what type of dry eye disease they have. In terms of the modeling side, there are extensions to the models that we could include. In particular, you could include de-wetting, which is where the ocular surface, a region of the ocular surface is repelling water, right? And that is going to also form breakup. So I want to just take one moment and shamelessly plug my current work because it is in a total different direction now that I'm a postdoc jointly at Johns Hopkins and NIST. So it is related to diagnostic classification. So if you think about COVID as an example, in the 1D setting, you want to take a known negative population where you've measured some antibody target. So these are people who have not had the disease, and look at people who are known to have had the disease, so COVID positive, for example. And what you want to do is you want to set a classification boundary so that when you have test data, you know what to classify it as. And setting this is not obvious. Okay? So if you set it here, for example, then any future test data to the left, you would classify as negative, and to the right, you would classify as positive. And something that we are working with is that the current methods don't account for the structure of the data, any sort of attributes that it has, different from the positives and the negatives, and the classification only takes into account the negative, mean, and standard deviations. So what we've done is we're introducing the idea of using modeling and using it at a very high dimension, or a higher dimension. So we have gone not from 1 dimension, not to 2 dimensions, but all the way up to 3 dimensions. And we have created these probability regions where we have contours where if it's darker, it's a higher probability. And we can better separate in this way our negative population, which are the blue diamonds, from the red X's. And we show that we're able to improve upon traditional classification results. This also is able to extend to more than 2 classes, and it works in arbitrary dimension. So that's something that I am currently working on, again, in a COVID context, but it has a very general framework. And I've been enjoying my current work so far, even though it is very different, but still very biologically relevant. So I'll return to my conclusion slide, and thank you for your time and take any questions.
Thank you very much. That is a very nice talk. So I'm going to stop the recording and